Alright guys, welcome back. Let's just get started. My name is Casey Campbell. I am the team leader of the Automated Small Parts Orientation Group, sponsored by Berry Industries. I had the pleasure of working with these three people here throughout the semester: Justin Barca, Nicholas Keene, and Marissa Cavallo. We are advised by Apsun. So a little bit about Berry Industries before we really get started with the project. Located close to home, Attleboro, Massachusetts. They are the top supplier to a lot of leading manufacturers, some of those being Raytheon Corp, Siemens, Airbus. They are ISO 9001 certified, which is basically a standard for quality manufacturing systems. I'll breathe for a second. They pride themselves on vertical integration. Basically what that is taking processes that would usually be done at different manufacturing sites and bringing it all into one. Everything is done in-house from production to delivery. They also pride themselves largely on customer service. So part of what helps them do all the deliveries on time is tape and rail loading, which is what our project has to do with. They follow the current tape and reel packaging standards in terms of orientation, as you can see on the bottom here. They have tons of different sizes of chips, some of them being 50 millimeters in length, which is pretty small. One we were asked to work with is the RZC 2010. It is 200 millimeters by 100 millimeters, pretty small. And as you can see on the tape, following the standard, the orientation strip follows the sprocket side of the tape. So when you think of endurability, repeatability, efficiency, you think robots. That's at least what we thought. Currently, they do it manually, orienting all these chips. Takes a lot of time, gets a lot of fatigue in the process, causes a lot of errors, a lot of paperwork, which costs them time and money. So what we decided to do was utilize the existing robot they already had. If you look in this little circle here, we have designed a tooltip that will help to facilitate the process of picking up, placing, and orienting these chips. And I'm going to pass it off to Justin to talk about the design.
Thank you, Casey. So in the early stage of our design, we came up with 3 separate prototypes. Option 1 being a claw mechanism, which grabs the chip, lifts it, and orients it. Option 2 was a suction tube design. Uses suction force to lift the chips and orient them. And option 3 was a rectangular prism with slightly greater dimensions than the chip, allowing it to encase the chip, orient it, and slide it across the table. We developed a decision matrix based on key factors such as simplicity, feasibility, cost, performance, and machinability. And we determined that option 2, the suction tube design, was our ideal choice. So we further refined our design in SolidWorks. The dimensions are roughly 4.5 by 5 inches. We've incorporated a Venturi, which uses compressed air to produce a suction force. The main components of our attachment are machined from aluminum 6061 T6. We chose this material based solely on low cost, lightweight, and machinability. Here's an exploded view of our design. We have the flange block, which bolts directly to the end arm of the robot with 4 bolts. We have the threaded rod, which threads into the flange block, and the tooltip, which is threaded onto the threaded rod. Also, we have the Venturi valve, which is bolted directly to the flange block, allowing it to rotate freely with the attachment. Berry Industries produces a wide variety of chips ranging in size, so we wanted to make our design interchangeable. Having this threaded rod allows tooltips to be machined with different diameters, allowing different chips to be picked up. As you can see in these pictures, the design is machined and assembled. Berry Industries had CNC machined our flange block, and we actually did some machining in-house. We did the threaded rod and the tooltip here at the machine shop at UMass. Another key feature of our design is this machine notch here you see circled. What that allows us to do is have the suction line and the air supply line run out through the flange and directly to the venturi. This allows our tooltip to be central to the robot, meaning it doesn't have to have a transformation from the center of the robot arm. I'd also like to point out that the diameter of the tooltip is slightly smaller than the smallest dimension of the chip, which prevents the chips from being sucked up into the tooltip and having a malfunction. Also, having this machine notch keeps all the air lines clean and out of the way of our process. And I'm going to hand it over to Nick, who's going to talk about testing and troubleshooting.
Thank you, Justin. So after the piece was machined and fully assembled, we decided it was time to actually put on the robot. It only requires 4 bolts and a couple of lines to be connected. It was very simple. So we started testing once it was on the robot. And our first form of testing was the pneumatic system, just to be sure that these chips would be properly lifted and released. Our second test was the robot actually goes through a standard calibration before, right after it's turned on. And during this calibration, it does all kinds of movements to make sure there's no obstructions, not hitting anything. And another testing method we did was testing the robotic speed. We wanted to see how fast it would move and make sure there was no issues with our pieces, whatever, coming loose, falling off. And then lastly, we looked into the camera, which had a very small workspace size. As you can see, that picture right here is of a chip. It was able to capture its dimensions, but this work area is just under 2 inches by 2 inches. You can't place many chips in there. And so as expected, we ran into a few issues with the testing. Our first issue was with the suction, as I explained. We were able to lift the chip successfully, but an issue we were having was the chips weren't releasing as fast as we would have liked when we released the suction. So in order to solve that, we drilled a 1/32 of an inch, very small hole in the tooltip right there, which goes into the suction system. So what was happening was something called airlock, where the negative pressure in the system was staying in the system, even though we released the air. And so, like I said, to solve that, we drilled a small 1/32 hole, and that actually helped it significantly. We didn't have that issue at all after. Another issue we had was during the standard calibration, as you can see right there, the camera and the tooltip would spin during the calibration, and the venturi would come in very close contacts, occasionally hitting the camera. So we decided to just relocate the camera a little bit. Just a small adjustment, it wasn't a big deal. Another issue we had was with the background color. We initially started with a white piece of paper, and one side of the chip was white, so the chips were getting washed out from the vision. So we decided to go to a more neutral color, which was more in between being white and green, because one side of the chip's green, the other side's white. And we ended up with a light blue, which worked pretty well. Lastly, Barry Industries actually had to relocate the robotic arm, and it was in the same room, but another location in the room, where there was significantly less lighting. We weren't really expecting that change. So in order to accommodate for the change, we installed a simple LED lighting ring. And after all these issues were solved for the most part, we did some final testing where we ran a 30-second run of the arm to see how many chips it would be able to lift and orient and place into the tape. And this proved, in 30 seconds we were able to do 10 pieces, which proved to be 50% faster or 50% more productive than the manual labor. Some other positives to this were there is no operator. The only operation that needs to be done is the chips need to be placed onto a table. So this employee could be working on other projects, and every hour or whatever, just bring a batch of chips and place it onto the table. Another thing is the arm doesn't require really any maintenance, so there's no cost there. And I'm gonna hand this over to, actually I'm gonna show you a quick video. It's tough without the sound, but you can hear the suction kicking on and shutting off. And as you can see, the suction obviously needs to release the chip really fast because it's hitting that location and moving away. So initially it was getting stuck and messing up the tape and running into a few issues. But ever since we drilled that ventilation port, just that little hole was able to release the suction and let the chip fall out. And that was 10 chips in roughly 30 seconds. I believe it was like 28 seconds.
Oh, there we go. All right. So after consulting with Barry Industries and getting a better idea of all the information for our test, we were able to move on during the beginning of the semester with brainstorming our ideas and coming up with our design. This led into ordering our parts and doing the machining of the tool attachment, which ended up taking up the bulk of our time. Leaving us with about a month and a half for the testing and troubleshooting. But pretty much all year we've been able to stay on task with our project. So we had an initial budget of $5,000 and we used 1% of that budget, giving us roughly about $4,970 left. The only costs that went into it were for the necessary parts for the tool attachment. And the reason for this was, since the beginning of the project, we had an idea of ordering a new camera, which can get very costly. What ended up turning out happening, unfortunately, it was too much and out of budget. But lucky for us, we were able to just use 1% of that budget. That leads me into our future recommendations, which would be a higher resolution camera. The benefits of this would be, as Nick had mentioned, we had to use an LED ring. So already having that new camera would have the lighting in it and be able to automatically focus without us having to make those adjustments to the current camera. We would be able to expand the workspace, allowing more parts to be on the surface. So it would be able to process more parts and just having an overall better efficiency with the location of the chips and the defects and orienting the chips into the tape. Another suggestion might be to have a more compatible software to go with that camera, as well as machining tooltips, as I had mentioned the guys earlier, for all the wide variety of size chips that Barry Industries does manufacture. Assuming that they do, though, stick with the current camera, we suggest that maybe a less reflective background, though we did find one, that can always be improved. So now I'm going to hand it over to Casey to wrap up our presentation.
So, as a team leader, it's important to delegate tasks in order to stay on time, make sure that nothing really impedes the next step in the process in terms of finishing this first, waiting for something else. So, these guys all did a great job with all the jobs they were asked to do. Like I said, team leader, I facilitated the project, helped keep everybody on task. I also like to get my hands on the machining process of it. Justin, all the SolidWorks designs you saw, that was all him. Did a great job with that. He also helped manufacture the parts. Nick was big on the whole troubleshooting process of it, as he showed in the slides. He helped a lot with the programming, also got hands-on with manufacturing. Marissa, she was big on the programming. She was in there typing like crazy all day, trying to figure it out. And she helped stay on top of all the materials we needed, top of the budget, hoping to save for the camera like we said, but it was out of budget. So, and that was all. If anyone has any questions.